simple, but let me pause here for 5, maybe 3 minutes and see if anyone has questions. Someone says, I was just wondering if we could do a Pearson correlation between changing cost of cement and cost of building homes. Thinking about it, is it not possible that the fact that the cost of new homes may not have strong implication? Okay, so this is definitely. Oh, someone says I can't see your screen. Oh, Rafiat cannot see my screen. Can everyone else see my screen?
Yes, ma'am.
Yes, I can.
You know, from time to time, people think that I'm female. So someone just said, yes, ma. You can see my video. Okay, great. Yeah, I like it. Okay, yes, Rafia, sorry, but yeah, maybe you might want to leave and join. Maybe I should wear earrings and that will confuse people more. Okay, are there any questions? Oh, someone said close the poll. So maybe Rafia. Oh, I'm so sorry about that.
That's it.
So someone says, can you explain positive and negative correlation? Okay, let's do that. So this is your, let me close this. So positive correlation, who's the person who said, can you explain? So let me call their name so that it feels personal. So Baveline, that's a nice name. I've never seen that name. So Baveline, in a there are 2 ways to look at a positive correlation. One is based on logic, the other is pictorially. So based on logic, if there is a change, if both things change in the same direction, then the direction is positive. And this brings a trick question. If there's a reduction in the price of cement leads to a reduction in the cost of homes, is that still a positive correlation? The answer is yes. As long as the direction is the same for the 2 variables, it is positive. So if you reduce your food consumption, your your BMI would reduce. So even though both of them are reduce, that is still a positive direction. The logic behind the direction of correlation, Baveline and others, is the direction between the 2 variables are the same. A negative correlation is that the direction is different. So if one increases, the other reduces, or if one reduces, the other increases, that is a negative correlation. Different directions is negative, the same direction is positive. Okay, and we said pictorially, this can be seen on a graph. You can see that, as you can see here, as this one increases from 100 to 125, this one is also increasing from 100 to about 125. And you can see here, negative correlation is as this one increases, this 120 here, this guy is at the lowest. When this guy is at the high, when this y-axis is at the lowest, you can see that you can find this guy. Wait, what's happening here? Okay, this guy's an outlier. But basically, this is a very weak correlation, so it may not be very clear, but the direction here is this way. Okay, positive correlation is somehow directly proportional and latter inversely. Wow, I don't understand that grammar, but Dr. Mataya says yes. So let's move to the, as they say in Nigerian comedy, Oga Pata Pata of them, or a simple linear regression. So let's talk about what a simple means here. So simple just means that you are looking at only one, predictor. And we're going to talk about what a predictor is. That's the meaning of simple. If you have more than one predictor, you are talking about multiple linear regression, or multivariable rather, not multiple, multivariable. So that's the only reason why it's simple, because there is one predictor. Okay, I'm going to say it again because it's going to confuse people. It confused me for like 3 years before I find out, maybe not 3 years. If you have more than one predictor, it is not simple. What makes a linear regression simple is that there is only one predictor. So let's talk a little about linear regressions. Okay, but before that, let's see. Oh, okay. So I moved this slide. Okay, I moved this slide, so it's my fault. Okay, so remember that I started and I told you guys that we're going to speed this up. We're going to take a break around 1 for 5 minutes. So let's do as much as we can before then. Remember what I said, that many times we see that studies from Nigeria and out of Africa kind of keep it simple. They do a correlation and then they publish results. And that's because sometimes there isn't enough statistical power, I mean human resources, to do more complex stuff. So we want to let you know that a correlation is not a linear regression. Don't do a correlation and submit your paper. Do a linear regression. If you can do a correlation, you might as well do a linear regression. So they are not the same thing. And going back to correlation, we spent quite a lot of time here. We're talking about direction, blah, blah, blah. And what you can see here is 0.75. This number is the correlational coefficient, but it's not exactly what you need when you're thinking about effect, when you're thinking about association. So keep in mind that it's a correlational coefficient, but we're going to come here. You see, if you read this, if two variables are correlated with one another, the value of one variable can allow you to estimate the value of the second variable. So when we were looking at that correlation thing, because you have 0.75, some people will think that if I tell you the price of a ton of cement, you will be able to tell me the price of building a home. That is not true. A correlation value does not help you do that. And some other people might say, well, if you are looking at the, if you're looking at the picture, you can see a BP of 150 here, and you can tell us the BP on the x-axis. That is also not true. It is not a correlation that does that for you. It is a regression. And the reason why someone said, are you saying a regression should always follow a correlation? Absolutely. If you do a correlation, just follow it on and do a regression if you have what the things it takes. And the reason why pictorially you cannot say that you can predict is look at this 150 line. Look at this one, there's something around on the line, there's another one on the line, there's another one here on the line, there are about 3 dots here on the line. So which one will you choose as the prediction? That is where a linear regression comes in. A linear regression helps you take what you call the line of best fit. So we're talking to, I can't remember who it was, but I said, if you draw a line through this place, no matter how tight this thing is, you can draw an infinite number of lines through, you can draw an infinite number of lines through these points. Does anyone agree or disagree? Let's ask someone on the panel. Let's go to Abbas. Abbas, were you added to the panel?
Yes, I'm
all right. So do you agree with me that you can draw? How many lines do you think you can draw through this graph?
I think 2.
2? Okay.
No, sorry, one.
Only one line. You can draw only one line. What of through this one? The one below.
Okay. This one can. It's a little bit confusing. But I can draw two here.
You can draw two where? Here. I have to mute myself while I blow my nose. Excuse me. Okay, Abbas, we're back to you. So you said you can draw only two lines here. You said you can draw one line here.
Yes.
And then you can draw two here.
Yes.
I see Ebube say you can draw multiple lines here. Josephine, tell us, how many lines do you think you can draw through the first one?
Okay, so for the first one, I feel as if you can draw nothing less than 5 lines. I think you can draw less than 5.
Does nothing less than 5 mean 5 or more or 5 or less?
5 or more.
5 or more. So it can even be up to 500.
Yes, because they all seem to. Okay, the second one, I don't think it will be a line of best. You can draw a line, but I don't think it will be a line of best fit at all. Because everything seems scattered.
Okay, I like that. So I think Josephine's answer is more correct than Abbas's answer, you know, because it is true. Do you know how thin a line is? You can draw a line anywhere on this point, and it would be so many. And the directions would also be so many, and even more on this place. And that is why you have to do a regression to find what Josephine is calling the line of best fit. And we're going to talk about that as we go on. So remember that you cannot predict the change with a correlation. You can only tell us if it is weak or if it is strong, but you cannot predict the change. Okay, so so another thing we want to talk about, remember when we said simple versus multivariable. Okay, show of hands, and by show of hands I mean click on the I think there's an emoticon. How many of you drink coffee? Or you can type it in the chat. You can just say yes, no, yes, no. I'll tell you a really good story, a real life story, and then we'll move to the next slide. Okay, Habib raised their hand. Yes, no, yes, I drink. No, no, yes. Keep going. No, yes, 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 no, no. B, Taiwo. No, it's too bitter. Put some milk, put some sugar, make it nice. Yes, no, no. Okay, so we see that some people drink, the no's are coming in, looking a bit like the US election. Some people vote later than others. Let me tell you a real life story. Before it became really popular to drink, can someone answer this question? What is particular? I think BE raised their hand. So let's talk to BE. What do you know about people who tend to drink a lot of coffee? So you see that public health is for real life critical assessment. So tell me, we've talked about cement, now we're talking about coffee. So is BE there?
Who are you asking? I don't think it's unmuted yet.
BE, Philip.
Philip. Okay. So I think you should be able to talk now. You can unmute yourself.
Okay. All right. Thank you for allowing me to talk. I think people who drink coffee usually have like a particular flavor of coffee.
Okay, I like that. Okay. So someone said they are workaholics. So can we try to understand maybe what other behaviors do they do?
Yeah, usually they always
Exactly. Someone tell me. So that's behavioral. What other behavior? That's clinical. What other behaviors do they tend to do? I'll tell you, because hyperactive. Someone said hyperactive. People who drink coffee, at least before coffee became a fashionable thing due to Starbucks, people who drink coffee tend to smoke as well. Okay, so some years ago, before coffee became fashionable, some physicians or some scientists did a study on coffee consumption and bladder cancer. And they found out that if you drank more than 2 or 3 cups of coffee per day, or maybe 4, you were likely to get bladder cancer. This was a very significant study. Of course, what's the implication? The implication is to reduce bladder cancer in your country, you have to either put a higher tax on coffee because you cannot stop people from drinking it, or you ask coffee manufacturers to put what they call a black box label, which is a warning saying if you drink this, you may get bladder cancer. However, some people went back and looked at that study and they found out that it's really not the coffee, but it's that at that time, people who drank a lot of coffee also tended to smoke a lot of cigarettes. It was the cigarette smoking that was causing the bladder cancer. And so it brings us to point 3. Point 3 says that you can adjust for confounding with a linear regression. So for example, when you see a strong correlation, you should not stop there. You should be wondering whether there are confounders, the way cigarette smoking confounded the relationship between coffee and bladder cancer, and a regression would allow you adjust for that. So this is really number 3, why you should not stop at a correlation, or why you should do a regression. And the other thing is, remember, we've been talking about Pearson's correlation and Pearson's correlation. But what we realize is that the Pearson correlation happens between 2 continuous variables. I'm going to spend 2 minutes. I'm trying to kill the clock till 1 o'clock when we go into the regression. But I want to pack this time with some knowledge. Okay, let's ask someone. Who's joining the panel for the first time? There's some people who raised their hands. I see Comfort Bowman. They're mostly unable to function without it. Okay, Comfort, unmute yourself. Tell me what a continuous variable is. And if comfort does not in fact, the person who said you can draw at least 5 lines or more is the person that should answer this question. So Comfort, unmute yourself. Tell me what a continuous variable is, and then you can tag the person who said 5 lines. I think it was Josephine, I can't remember. Okay, so, yeah, Comfort may not be able to unmute herself. That's okay. Anybody else? Even though we're trying to keep time, we just have 2 minutes. Okay, I'm going to ask this question differently. And please, any of you who can unmute yourself, answer. What is the distance between 1 and 1.1?
Comfort, you can speak now, actually.
Someone says age is an example of continuous variable. Okay, so a variable with a true 0. So Toluwani, not really, because what we're talking about is intervals and ratio variables. Both of them, even the ones without a true 0. For example, Fahrenheit does not have a true 0, right? But it is still because you can have -2 minus 273. Someone said height. I'm not asking for examples. I'm asking for the definition. I said, what's the difference between 1 and 0.1? And someone said it's 1 and 1.1. And someone says 0.1. But I didn't say what's the difference. I said, what's the distance? Taufik gave us the answer. Taufik, can you unmute yourself, Taufik Alabi, and tell us what the answer is? What is the difference between, what is the distance between 1 and 0.1? Taufik, let's do it. We won't take a break at 1, so unmute yourself quickly and tell us what your answer is. You put it in the chat. Okay, Taufik does not care about the time, so I'll tell you what's the answer. So he said the distance between 1.0 and 1.1 is infinite. infinity, because you can have 1.001, 1.001, 1.00, all the way. And that is your definition of that is your true definition of a continuous variable. The distance between 2 points is infinite. So if they ask you about the teeth in your mouth, some people will say that's a continuous variable. But really, technically, it's not a continuous variable because you cannot have 31.999 teeth, right? So that is discrete and it's bound. You can have maybe between 1 and 40 teeth in your mouth, but you cannot have 35 points. I mean, you can have a half tooth or a quarter tooth. You know, we're going into semantics now. When you do a Pearson's correlation, you're doing a correlation between usually between two continuous variables. And remember that in statistics, you can bend the assumption. So someone will say, okay, let's call teeth because there's up to 32. Let's call it continuous, yes. But the real definition is continuous. It says an infinite number of points between any 2 points in that variable. So blood pressure, your blood pressure can be 100.1, 100.11, 100.111, 100.1111, goes into infinity. Okay, when you do a Pearson's correlation, you're doing between two continuous, but in a regression, even when your variables or one of your variables is not continuous, you can do a regression. So you may not be able to do a correlation with categorical variables, purple, red, blue. No, that's nominal. Old, older, oldest. But you can do so with a regression. So let's take a break for 5 minutes. We'll come back and get into the meat of a linear regression. I'm going to mute myself and go water my plants. See you back in 5 minutes. Okay, we are back. So let's answer quick questions. And someone said, someone asked a really nice question. We're going to jump into it because of time. So someone said, does it matter if one is the dependent variable and if the other is not the dependent variable when we are looking at, what's the word? When we're looking at regressions? Yes. So remember that we call this a linear regression. So when we were looking at this, I told you the meaning of simple. I didn't tell you the meaning of linear. Linear means we are trying to predict a continuous variable. So the dependent variable, which is what we are trying to predict, has to be linear, has to be continuous in a linear regression. There are other types of regressions. There's the logistic regression, but we won't deal with that, maybe not in this course. There's the Poisson regression. There are other types of regressions that they're really just derivatives of the linear regression, you know, depending on how you bend your assumptions. So remember I said in statistics, you bend assumptions a lot. For example, even though the teeth in your mouth is a discrete variable, some people would say, well, you know, we can assume that it is continuous, and you model it. If you want to predict how many teeth you have in your mouth, that would be a waste of funds, but if you want to do it, do it. So we're here. Okay, so this is why I wanted us to do this after the break, because someone said I can't hear him. It's because we're on break. If you're conducting a longitudinal study, the independent comes first. Okay, so that's Dr. Omotayo and responding to the question. So yes. Okay, by the way, big ups to Dr. Omotayo. Thank you so much for facilitating this. Dr. Omotayo is a lot smarter than me, so shout out to him. Okay, so I don't know if you guys remember your mathematics. This thing always gave me problems in school. I really, you know, one of the reasons I became a doctor was because I didn't like math. Can you imagine? So you know, in JAMB in Nigeria, you have to take math, or English, you have to take English, but you do math, physics. I preferred physics to math. So I just took that and became a doctor instead of an engineer. I might have been a terrible engineer because if you know me, I bounce around a lot. Maybe it's the coffee. Okay, so let's talk about this thing a little bit. And you said this formula is just following us. I'll go follow you everywhere you go. So let's talk about this a little. So you see here, you have the x-axis. In statistics, what you do is that you use x to predict y. And there's a concept called bidirectionality. Remember that in correlation, you say when one increases, the other increases. You don't care which of them is causing the other to increase or reduce. That's another difference between regressions and correlation. The correlation does not exactly tell you, not direction. If correlation tells you directionality, but it does not tell you temporality. Temporality means which of them must happen first for the other to happen. So for example, we know that if you eat food, you get satisfied. You can do a correlation between satisfaction and the amount of food you eat, but it's not going to tell you about temporality, which means that you cannot say that your satisfaction causes you to eat food, but you can definitely say that eating food causes your satisfaction. So eating food must always be on your x-axis because it is your predictor. And that is why it is called your predictor, it is called your explanatory, or it is called your independent. Independent, don't confuse this with dependent. It's called explanatory because it is the thing that explains your dependent variable, not your independent, but your dependent variable. So you cannot say that, you cannot say that being satisfied causes you to eat food, even though they are correlated, even though they are positively correlated, and even though that correlation is strong, you must do a regression that shows that explain satisfaction using a predictor. So you can predict your satisfaction through how much food you eat. That is why it's called predictor, and that is why it is called explanatory. It is what explains the other variable. Okay, why is it called independent? I don't know, but just learn it. Independent is your X, dependent is your Y. It's also called your response. This is what responds after you activate your predictor. So you cannot say that, for example, let's use a more public health, smoking causes lung cancer. You cannot say that, oh, a person, because they are correlated, you cannot say that a person who has lung cancer will smoke. No, but you can say a person who smokes is likely to have lung cancer. So that is temporality, and that is a little bit of directionalism is there as well. Okay, so we've explained X and Y. Let's explain the M. So now, what if I tell you that money can actually buy happiness? You know, people say money can't buy happiness. Okay, maybe. But what if I tell you that at least to a certain degree, money can buy happiness? For every 10,000 naira or pounds or euros you receive, your quality of life, including happiness, would increase by 0.2 Q. Let's call Q happiness, or H, 0.2 H. For every $10,000 you receive, your quality of life or happiness will increase by 1 H. That 1 H is your M. And remember, from mathematics, it's your slope. It basically explains how both of these things are related. And it is not the same thing as your 0.5 in your correlational coefficient. It is your unit of prediction. For every spoonful of jollof rice you eat, your satisfaction increases by 0.1 units. That is the unit that explains your relationship. It quantifies, because your correlation also explains it, but this quantifies how they are related. Okay, the last thing to talk about is C. So let's talk about happiness. Let's imagine that money can buy happiness. Are we saying that a person with 0 euros or 0 pounds or 0 shillings would never be happy? No, that's not true. Even the poorest of poor people afford to smile and find happiness from day to day. And that is why you have a constant. And that is why your line does not typically start from 0. They just show us that in primary school arithmetic to keep us happy. But in real life, there is an amount of Y of your dependent variable that all human beings will have, irrespective of the amount of their X. That is why a regression line typically starts not from 0, but from a constant. And sometimes that constant can be negative. Okay, so I've explained this. If you have questions, you can raise your hands and let's move on. But this is mathematics. And someone said this formula has followed us. It follows us and it also grows. The same way you grew up, that's how the formula grows up. In statistics, instead of being written like this, 2 people have raised their hands. Someone said, can I come again? Can I explain this again? Okay. Should I do that? Let's try. Okay. So you remember this formula? I'm assuming you remember this formula. If you don't remember it, I'm so sorry. So there are 3 things that we have to talk about in this formula. Number 1 is temporality in regressions. In regressions, you consider temporality. And we use smoking and lung cancer. A person who smokes, you have to smoke first before you get lung cancer. And someone's going to say, well, there are some people who don't smoke and they get lung cancer. We're not talking about those people. We're talking about people who get lung cancer from smoking. You have to smoke first before you get lung cancer. That's temporality. One must happen before the other. A correlation does not tell you about temporality. A regression does. The thing that must happen before the other response is called the predictor, the explanatory, or the independent variable. Your smoking would explain why you got lung cancer. And those things are usually, mostly, in fact, all the time on the x-axis. That is why we call x your predictor. It predicts if you smoke, you get lung cancer. It will predict whether you get lung cancer or not. That's why we call the axis x your predictor, your explanatory, or your independent variable. Your y, remember I said earlier that I don't know why it's called independent variable. That was a lie. Your y variable is your response, is what responds. So if you smoke, your body will respond to your smoking by either getting lung cancer or not. So your y is always your dependent variable. And it depends because your getting lung cancer depends on your smoking. In the population of people who get lung cancer from smoking, they will not get lung cancer if they did not smoke. Getting lung cancer depends on smoking. That's why it's called your dependent variable, and it is your y. But the other, your x, is independent because your getting lung cancer cannot cause you to smoke. Somebody will say, well, I know some people, once they just got lung cancer like this, they just say, okay, I'm going to just spoil the rest of my life by smoking. That's not what we're talking about, you know. We're talking about scientifically. And we said your slope is now where your correlation kind of differs. Differs your correlation from your regression. Why? Because it tells you, it quantifies the unit of change. It quantifies your unit of change. So you see, if you smoke, and for those of you who are physicians and nurses, you would remember that they would say, when you ask a person, do you smoke? You don't just say yes or no when you're taking a history. You have to ask how much and how many packs a day. Why? Because we can quantify your risk of getting lung cancer. For every 1 pack of cigarettes you smoke in a 10-year period, your risk of cancer increases by 0.5%. That is your M. Your slope is telling you how much of your X must happen before 1 unit of your Y changes. For every 10 packs of cigarettes you smoke in a 1-month period, your risk of getting lung cancer increases by 1 unit. That is your slope. It's called your M. Your constant is simply that just because your X is 0, your Y will not be 0. And we talked about money and happiness. Even if you have 0 money, does not mean you will not be happy. So there is a amount that even when your X is 0, your Y will still be operational. This is very important. But if you understand it to the extent I just said it, we're fine. Okay, let's move on because of time. And I said the formula graduates. So you see this formula, y equals mx plus c. It becomes y equals alpha plus beta x. Remember that we said if you use Greek, you're talking about population. If you use Roman numerals, you are talking about sample. Remember what I said, that research science is for decision making. And the reason why you begin to use Greek numerals is because you want to extrapolate to the population, not just your sample. When we talk about the interpretation of your regressions, we're going to talk about your extrapolation to a population. You're going to talk about extrapolation to a population. I'm going to say it one more time because you will forget it. When you do research science, you are extrapolating from a sample to the entire population. Okay, lastly, there is an error term. And I want to show you something quickly in the error term. Look at this. Remember when we said if you're at 150, there are so many points on this line. that you cannot predict. When you use a line of best fit, we started talking about a line of best fit earlier, there will be a point that you think is the best fit. It does not mean that other points on that line are wrong. It just means that there is some error term, you know, and we're going to talk about it. Let's move on. Let's roll this poll for 1 minute, and then I will try to look through the questions. Grace, I hope I answered your question, but